paper discussion about world model development, which is independent of the actual surrogate actions of the robot. In other words, we want to develop, the authors are developing a world model that can be applied to any kind of computer tasks. So you're not testing the world model by testing whether it can actually do something, whether the robot can grasp a bottle or pick up a tray. You're developing a world model that is good at predicting actions of the robot within the world, the virtual world and hopefully the real world, independent of the planning of the actual reinforcement learning algorithm that teaches the robot how to plan. So there's a separation of world model and planning, which hopefully will get to a point where we can have a foundation model for robotics. Now, the authors aren't talking about this. This is a more technical focus on the world model itself, but I think this paper sort of fits into the broader literature of foundation models for robotics, because what it's trying to do is generalize world model development and also generalize reinforcement learning as a planning tool for robots. This is not even on podcast. It's April 18, 2025. This is Krim Delco. You were down 42.9%. The market's down 10.4%. We're underperforming by 32.5%. So the paper out of UC Davis and the Open Path AI Foundation is the title Neural Motion Simulator, Pushing the Limits of World Models in Reinforcement Learning. The paper's attached to the show notes. So the key components of this paper are that first, there's a technical approach towards world modeling, which is a physics-based rigid body force distribution, the neural ordinary differential equation dynamics. Those are technical. Those are technical. It's a technical wrap to actually teach a model how to move in nature. Now, what that means in practice is first you're using real physics. Like, for example, you have a rigid body, you have an arm that has a certain length, and you can define how that arm moves around in space. Like, that's predefined by physics, by things like rigidity, inertia. This arm will move differently in water than in air, things along those lines. And then you have the neural ordinary differential equations, which is what the neural means is that within the differential equation system, you have dynamics. You have, let's say, partial derivatives of motion, of velocity, of actuator forces. And those dynamics, they are parameterized in a neural net. So they're learned. And that's the key. So this is an innovation that goes back to 2018. Links are, again, in the show notes. I don't want to, this is not a technical podcast in the sense that we're going to now talk about the math and things like that. What we're interested here is applications for robotics that can be actually translated into products and services. The purpose of Orange Capital Partners is to invest in fundamentally new concepts and engineering practices with large impact. That's what we do, and robotics is our main focus because we believe that that is a fundamental engineering discipline now that has the potential to create a lot of wealth. So why are we interested in a paper like this? Maybe just to give people a bit of a sense for new listeners, why are we talking about scientific paper? We're not a scientific paper review podcast site or anything like that. There's much better sites for that. What our attempt is to steer our listeners towards two things. One is actual scientific interesting papers that could be interesting for technological advancements, but more importantly, also we're really interested in conveying the message that knowledge creation has a very large state space. Like, you can read books, you can read scientific papers, you can go to conferences, you can talk to people, you can You can try to get inspiration from novels. We do all of the above. And I think that's just our approach towards the hedge fund business. It's one of, maybe this is the ultimate knowledge business, right? It's very intangible in the sense that we never build things. We try to accumulate knowledge about where wealth creation is heading towards, and we do that by understanding technologies, but also the people who actually do those technologies. Now, this paper is really about the technology. So let's talk about the paper. World model is another word for, can we give the robot an understanding of the space that it's moving inside and how it's going to move inside that space. So we're not talking about grabbing a tray or emptying a trash can yet. We're not talking about that. What we're talking about is, does the robot have an understanding of where it is and how it's going to get from A to B? That's the world model. And the way it's trained in this particular paper is with tools such as rigid body physics and neural ordinary differential equations. These are fancy words for, we use priors from physics, like F equals M times A, things like that. Priors from physics, as many as we can get. So we can get very fancy also in that sense. I'm going to talk about this in a second. And then we also use differential equations to model the dynamics, but we don't, we actually use the parameters for the dynamics. We train them from a neural net. This is maybe the biggest innovation here. Now let's talk about what we mean with rigid body physics. So when we have an arm, a robot arm, we can model the movement of that arm in space. No matter what space it is, whether it's air or water or on Mars, these things can be modeled because we have all the priors. We understand gravity, we understand friction with air, friction with water. We understand these things. We have priors. So now we could learn them too. We can actually start with total zero priors, but we don't have to. So what this paper is doing is using some physics priors. And then the differential ordinary equations, they are defined with partial derivatives that represent the dynamics of the system. So how does velocity change? How does this change? How does that change? And all of these things can be parameterized in a neural net. That's what neural ordinary equations actually mean. So that's one of the big contributions of the paper. The other big contribution of the paper is the eval. So now we have a system that models the behavior of the robot. Now we have to train the robot how to behave in space, and we can use virtual space, either ISAC Gym by NVIDIA, or something that DeepMind also offers. I'm not 100% familiar with their technology, but it's the same thing. It's think of it like a physics virtual engine, and the robot can move in that and learn how to behave based on the rigid body physics and the neural ordinary equations I just mentioned before. Once we have all that, we have now a world model that is trained on actually moving around in the virtual world. Yet we're not, the real to sim is a different problem we need to solve. But we have found a way to train the model without the surrogates. What that means is that we don't train the robot how to pick up a bottle yet. We train the robot how to move in space without having been given a specific task. And now we can decouple that from the actual specific task. Now we can train the robot, okay, now that we know how you move around in the real world, now go and pick up this bottle, go and move around, go do this, go do that. And the advantage of that is, in a nutshell, what we can do now is kind of like self-play. Now we can have the robot move in virtual space millions and billions of times and learn how to pick up stuff and do things. And I think that's roughly what's going on right now. I mean, this paper, I don't know how novel it is, and I don't know how unique and things like that, and whether they deserve the best paper award at NeurIPS or any of that stuff. But I've just thought it's an inspiration, because this is, in my opinion, where the world is going in terms of robotics, right? We have better and better world models and better reinforcement learning algorithms. And if we can separate those, we can have a very good world model. And then on top of that, a very good reinforcement learning algorithm. Then we can actually get somewhere with robotics and have a foundation model for robotics. That means we can task independently, learn how to move around in space and execute tasks. So to summarize, this is a good, I think this is a good example of a technology that we think is really getting to a maturity level now that can translate into real products and services. One of the biggest problems in robotics is the data scarcity, right? We don't have data, we don't have an internet scale information about actuators relative to actions. So what I mean with that is, let's say when we take Tesla and the FSD, we have videos of driving Teslas that are directly related to the actuators of the gas pedal and the steering wheel. We don't have that for anything else in robotics at scale. And what we can build is maybe a virtual database of this type of information. So when the robot moves forward, this is how the actuators are. When it turns around, this is how they are. Now, of course, there's a lot more to learn there, because one thing is how the world model, there's just two, if you will, there's two dimensions of the world model. One is how does the robot move in the world, and then how does the robot interact with the world? So how does it, what does it mean when the robot hits a rock? What exactly happens with the physics there and the dynamics? So those are, of course, unsolved problems. But I think the path that this paper is showing is the right paper. The right path. Thank you.